So let's continue talking about the normal distribution or that smooth continuous density curve. So in the previous lesson, I demonstrated how we could look at a continuous variable, particularly time. And we said that time is continuous. So if we were to continue measuring time to a finer degree, such as to the nearest hundredth of a minute or a thousandth of a minute, and so on and so forth, the rectangles are going to get more frequent and narrower, eventually approaching this smooth curve. And this is called the probability density curve, and we said it represents a continuous variable. And when it's smooth, bell-shaped, symmetric like this, we call it a normal curve or the normal distribution. So let's first talk about the characteristics of a continuous probability distribution. And we started to in the last lecture, but let me sketch a picture. So I'm going to go over to the whiteboard. So imagine we have this smooth continuous density curve that represents a normal distribution. And let's say so whatever my continuous random variable x is, right? So that's going to be labeled on the horizontal axis, whether it's time, height, weight, whatever the continuous variable is. Let's say I wanted to find the probability that x is between A and B, where A and B are just two values of the random variable. So if I wanted to find the probability that X is in between A and B, right? That's how I'd write it using math notation. X is between or less than or equal to B, but greater than or equal to A, right? So between. We said in the last video that this would just be equal to the area under the normal curve, right? So whatever this area is under this normal density curve, that would be equal to the probability. The other thing that I talked about is that the total area under the curve is always equal to 1, right? So imagine if we have a probability histogram. And if we shaded in all the rectangles, right, this total area is equal to 100%. So total area under the curve is always equal to 1 or 100%. And just a quick reminder as well, any probability, so the probability of x, right, always has to be between 0 and 1. So the probability of x always has to be between 0 and 1. And that goes back to what I taught you guys in chapter 5, right? One of the main characteristics of probability is that the probability of an event always has to be between 0 and 1. So that's these three characteristics that are listed under characteristics of a continuous probability distribution. I just put them in the picture for you in the whiteboard. So the probability that the continuous random variable x will assume a value between A and B, it's just equal to the area under the curve between A and B. The total area or the total probability under the density curve is always equal to 1 or 100%. And the probability that the continuous random variable x will assume a value between any two possible values always has to be between 0 and 1, right? We can't have a negative probability and we can't have a probability greater than 1. So let's get into the characteristics of the normal distribution. So we already said that a normal distribution now represents the values of a continuous variable. And the importance of a normal distribution is that it serves as a good model in approximating many distributions of real-world phenomena. So in other words, many real-world variables follow a normal distribution. And if a continuous variable is said to be approximately normal, then we can use the normal distribution as a model for that continuous variable. And we said the graph of a normal distribution is a smooth, symmetric, bell-shaped curve with a single peak at the center. And just some examples of distributions in real life that can be modeled by the normal distribution are IQ scores, adult weights, adult height, blood pressure of men and women, the size of red blood cells, so on and so forth. So there's many real world phenomenon that are going to follow a normal distribution naturally. So we've kind of talked about some of them, but let me just briefly go through properties of a normal distribution. So we already said the normal distribution is bell-shaped, symmetric, has a single peak located at the center. And I actually talked about this in chapter 3, that whenever we have a bell-shaped symmetric distribution, the mean, the median, and the mode all have the same value or approximately the same, and they're located in the middle of the distribution. So the normal curve is symmetric about the mean, and all the data values in the normal distribution cluster about the mean. Now, theoretically, the normal curve extends infinitely in both directions, getting closer and closer to the horizontal axis, but it'll never touch because it's continuous. So as the normal curve extends out away from the mean and gets closer to the horizontal axis, the area in the tails is going to get very, very, very small, very close to zero. And again, we said that the total area under the normal curve is equal to 1 or 100% if we want to write it as a percentage. So these are the main properties of a normal bell-shaped symmetric distribution. So now what I was saying in the previous lecture and before is that we can find these areas under the normal curve using a table, and it's called the normal table. And what I explained in the last video is that calculus can be used to find any area under the normal bell-shaped curve. And you don't have to know calculus, that's fine. The table was already created, but I just like you to know that these values, weren't made up or, they didn't come out of thin air. All these areas under this normal standard curve is based on calculating the area under the curve using calculus. Now, think about how many variables there are that are continuous in real life. I mean, there's more than we could count. Height, weight, age, time. There are so many variables that are continuous. So we don't have a normal table of areas for each different variable, right? There'd be too many tables. So we have a single table that's going to give us the proportion of area under any normal curve. But how is that possible if they're all different units, right? Like time is in minutes or seconds or hours, weight could be in pounds or kilograms. So how do we have this one normal curve that's going to represent the area, right? And we could apply that to any continuous random variable. Well, we have to standardize. And this is why chapter 3 was important when I taught you guys how to find z-scores. Remember what a z-score does for us. A z-score tells us how many standard deviations away from the mean a data value is. And when we convert a data value to a z-score, there are no units. The units disappear, and it's just standard deviations, right? How many standard deviations is that data value away from the mean? So although there's an infinite number of normal curves, there's one special member of the normal distribution family that we could use to serve as the normal distribution model for any application. And we call this the standard normal distribution, where all the scores are in z-scores. And the mean is equal to 0, and a standard deviation is equal to 1. And we need to use the z-score formula to convert any normal distribution to the standard normal. So we're getting rid of units and we're putting everything in terms of z-scores. And here's just a review of our z-score formula. And we have this one table, the standard normal table, that we're going to refer to in order to find areas under this normal density curve. So I'm going to teach you guys how to use this normal table. And you have the normal table in Brightspace. I have a PDF version linked for you, and I'm going to display mine. It's also in the book. So I'm going to teach you how to find a proportion of area under the curve. So I think the easiest way to do this is let's look at example 1. So example 1 says, sorry, dogs are barking. It was bound to happen. We got through 7 chapters, I think, without dogs barking in the background. In a normal distribution, let's find the proportion of area in A less than a z-score of negative 2.13. So I'm telling you right now, for every single normal distribution problem that we do going forward, I always want you to draw a picture. It's very easy to make a mistake if you don't draw a picture. So let's sketch a normal distribution. We know what that looks like, right? So we're going to sketch a normal distribution, bell-shaped. Now the mean always goes in the center, right? But we're going to talk in terms of z-scores. And we learned in chapter 3 that the mean of a distribution in terms of z-scores is always equal to 0. So 0 is going to go in the center. So you could think of this horizontal axis, the units are z-scores. It's just a number line of z-scores. So a z-score of negative 2.13 is going to be to the left of 0, right? So let's say this is a z-score of negative 2.13. I want to find the proportion of area less than a z-score of negative 2.13. So less than is going to be to the left, right? So let's shade the area to the left. So all these z-scores are less than negative 2.13. And remember, this is a continuous curve. So this curve is never going to touch the horizontal axis, but it's going to get closer and closer and closer. So we can very easily now find this shaded area underneath the curve, this proportion of area, by using this normal table that I'm going to teach you how to use. So you all have a normal table. I'm going to share my normal table. And there's 2 sides to the table. There's a positive side and a negative side. So you'll see the first side is negative. So you see how there's a z-score here, and then all these z-scores are negative. So that's how I know I'm looking at the negative table. And then if you scroll down and look at the other side, this is the positive table because all these z-scores are positive. So in this case, we're working with a negative z-score, right? You see how we want to find the area to the left of a z-score of negative 2.13. So I'm going to be on the negative table. So here's how the table works. Z-scores are always going to go 2 places to the nearest hundredth. So in the column underneath Z is going to be the number in the 1 spot and the 10th spot. That's this column. And then in the row on top, you're going to look for the second number in the decimal spot, the 100th spot. So if we want to look up Z equals negative 2.13, I'm going to look up negative 2.1 because that's the ones in the 10th spot. And then the 3 is in the 100th spot, so I have to look across the top and find the number in the 100th spot. So that would be a z-score of negative 2.13. And then we go to where they meet. So you see how they meet right here at an area of 0.0166. And that's the proportion of area to the left of the z-score. And you really can't forget because it gives a diagram on top and it says, this table represents the area under the standard normal curve to the left of the z-score. So that's how this table works. So the area to the left is going to be 0.0166. That's the proportion of area, 0.0166 to the left of a z-score of negative 2.13. So before we go to part B, let me give you another example. Let me make up another one. I'm going to go to the whiteboard. What if I wanted you guys to find the area to the left of a z-score equal to positive 1.76. So what if I wanted this shaded area under this continuous curve, the area to the left of a z-score of positive 1.76? So I'm going to go to the table. Now I have to go to the positive table because we're looking for a z-score of positive 1.76. So I'm going to look up 1.7, and then I have to look up a 6 in the 100 spot. And then I have to see where they meet. And they're going to meet right here at 0.9608. So that's going to be the area to the left of a z-score of 1.76. So 0.9608. So that's this shaded area under the curve. It's equal to 0.9608. So let's go back to the example. Let's look at part B. So part B says, what's the proportion of area greater than a z-score of positive 1.54? So I'm going to put my z-score of 0 in the center, and then a positive 1.54 is going to be to the right of 0, right? Because it's positive, and we want greater than. Greater than is going to be the area to the right. So we're looking for this shaded area under the normal curve. So let's go to the table, right? We always have to go to the normal table in order to get the shaded area. Now we're positive, so I'm going to stay on the positive table. And we want to look up a z-score of 1.5 and then 4. So I'm going to look for the 4 in the 100 spot. And they're going to meet right here at 0.9382. So remember how this table works. This table only gives the area to the left of the z-score. And you could see that in this picture, right? This is the area shaded to the left of the given z-score. This table does not give the area to the right. It only represents the area to the left. So this 0.9382 is this area right here to the left. 0.9382 is the area to the left of a z-score of 1.54. But that's not the area that I want, right? I didn't shade the area to the left. I shaded the area to the right. But don't worry, it's not the end of the world, because remember one of those main properties that I keep stressing about the total area under the curve. The total area under the curve is equal to 1. So this shaded portion plus the non-shaded portion, they should add up to 1, right? So if I know the non-shaded portion, I could take that away from 1, and it's going to leave me with the shaded area. So anytime we want the area to the right of a particular z-score, and we're going to use the table, you have to subtract the area to the left from 1. And we're going to get 0.0618. That's going to be the area greater than a z-score of 1.54. So before we get to part C, let me give you another example. What if I want the area to the right of a z-score of negative 2.05? So let's say I want the area to the right of a z-score of negative 2.05. So I have to go to my negative table. So let's go to the normal table. And we're going to go to the negative side now. And we want to look up a z-score of negative 2.0 and then a 5 in the 100 spot. So we're going to look where 5 is up top, and then we're going to go to where they meet. And that's going to be 0.0202. But don't forget, that's the area to the left. This 0.0202. It's the area to the left of negative 2.05. But again, not the end of the world. We just have to subtract this area from 1. So we're going to do 1 minus 0.0202 in order to get the area to the right. So we're doing 1 minus 0.0202. And we get about 0.9798. And that would be that shaded area to the right of a z-score of negative 2.05. And let's do part C. The last part of this question is asking us to find the area between a z-score of negative 1.08 and a positive 2.36. So we want to find this shaded area in between. So the way we're going to get an area between two z-scores is we're going to look up both z-scores and we're going to take the difference. So look up the larger z-score first. The larger z-score is 2.36. So let's look up 2.36. So we're going to go to the positive table and we're looking up 2.3 and then 6. And we get 0.9909. So we take the area to the left of the larger z-score. And now what we're going to do is we're going to subtract the area to the left of the smaller z-score. So now look up the smaller z-score, which is the negative 1.08. So I'm going to go to my negative table. So negative 1.0 and then 8. And that's going to be an area of 0.1401. So we have to take the difference. So we're going to take 0.9909 and subtract 0.1401, and we get 0.8508. And that's the area in between, the shaded area in between these two z-scores. So that's how we use the normal table. It's not difficult. Once you get the hang of it, then it just starts to flow. What's nice about the normal table is that it's already programmed into your calculator, the TI-83 or the TI-84. So honestly, you don't even need to use the normal table if you don't want to. If you want to go right to the calculator and find these areas, I'm going to show you how to do that in the next lecture. But I always have some students that love using the table. They don't want anything to do with the calculator when it comes to finding the area under the curve. So it's totally up to you, whatever you're more comfortable with. But I will tell you that I use the calculator. Honestly, it's just technology. It's going to be faster. It's less likely you're going to make a mistake, and you don't have to worry about always having that table near you. So going forward now, I'm going to show you guys how to use the calculator to find these areas under the curve. But if you prefer to use the normal table, then do so. So in the next video, I'm going to show you guys how to start using the calculator to find these areas under the curve, and then we'll do some application questions.